In this question, it says, consider the following reaction. And it says the plot of ln of x versus time gives a line with a slope of negative, this negative is down here, 8.21 times 10 to the minus 2 per second. So we have an ln of concentration of x versus time, and we get a line. And the reaction only has one reactant. So we're looking for, first of all, the rate constant. Well, first of all, it may be better to answer question 2 first, which says what is the rate law for this reaction. And in order to find the rate law, we need to determine whether it's first order, second order, or zero order. So 0, first, and second order. And here we have the integrated rate laws for those three expressions. And if we think of them as y equals mx plus b, what we find is that if we graph concentration of A versus time as y, concentration A at some time versus as y versus time as x, and we get a straight line, then the reaction is zero order. This is another way of determining the order of a reaction with respect to specific reactants. If we graph the ln of concentration of A at some time as y versus time, and we get a straight line, it's first order. And if we graph 1 over the concentration of A versus time as y and x, then it is second order. So basically, the y value is the one on this side of the equal sign, and the x in all cases is time. In all cases, the slope has something to do with k. In the case of a zero order and a first order, m, the slope of the line, is negative k. In the case of second order, m is just k. It's positive. So that is basically how we can use these integrated rate laws. We also have the half-life equations here, which we'll use later on in these questions. But in this case, let's look at the rate constant for the reaction. Well, since we graphed ln of the concentration of x versus time, where y is the ln of concentration of x and x is time, we know that this is a first order reaction. Well, if this is a first order reaction, m, the slope, is negative k. So if the slope is negative 8.21 times 10 to the minus 2 per second, the k is the negative of this, or positive 8.21 times 10 to the minus 2 per second. So the slope is negative k. Since the slope is negative, the k is positive. K is always positive. What is the rate law for this reaction? Well, since this is a first order reaction, rate equals k, concentration of x, to the 1, or we just don't show it. So in this case, rate equals k, concentration of x for this first order reaction. This next question is, what is the half-life of this reaction? Well, for that, we need to use the T1 half equation. Since it's a first order reaction, we want to use this T1 half equation. And note that this is the most useful T1 half equation because it doesn't have anything to do with concentration of A at time 0. So the half-lives of a zero order reaction and the half-life of a second order reaction change as the concentration of A changes. But for a first order reaction, the half-life is constant. Remember that the half-life is the time it takes for half of the reactants to become products. So in this case, the half-life is T1 half equals 0.693 over K, or 0.693 divided by K, which is 8.21 times 10 to the minus 2. When you do that math, you find that the half-life is 8.44 seconds. So this is a very short half-life. In 8.44 seconds, half of X will have formed Y and Z. The next questions involve using the integrated rate law. So the first one is, if the reaction starts with X of 0.1 molar, what is X after 1 minute? Well, it's important to note that our K is equal to, let me find it here, 8.21 times 10 to the minus 2 per second. And this is 1 minute. The time units have to be the same. So we need to change this to 60 seconds. We now want to use the integrated rate law. In fact, this is what makes the integrated rate law useful. The integrated rate law allows us to predict what the concentration will be after some time. The rate law expression doesn't allow us to do that, but the integrated form does. So in this case, we're trying to find the concentration of A at some time. So let's plug in what we know. Well, first of all, the ln of the concentration of A at some time is our variable, equals negative K 8.21 times 10 to the minus 2 per second times T 60 seconds plus the ln of the concentration of A0, which is 0.100. So we can plug in these things. Now, we need to do the math. Well, in order to do the math, I'm going to first take the ln, and I guess I'm going to put a concentration of X. This should be X, because that's what we're actually looking at in this reaction, equals negative 8.21 times 10 to the minus 2 times 60, which is going to be negative 4.926, plus the ln of 0.1, which you can just do in your calculator, which is negative 2.303. So we're adding two negative numbers together. Then, continuing, the ln of X at some time is equal to negative 7.229. Now to get rid of the ln, you use the shift or the second key on your calculator, and you take e of both sides. E to the ln is just the concentration of X at some time. It gets rid of your ln. E to the negative 7.229 you do on your calculator, and you find that X is 7.26 times 10 to the minus 4 molar. So we started off with 0.1 molar X, and after 60 seconds, which is many half-lives, we find out that it's very small concentration, 7.26 times 10 to the minus 4 molar. So the concentration has dropped dramatically in those 60 seconds, which again is several half-lives. The final question is what is the concentration of Y and Z after 1 minute? Well, if all of the X was used up, because remember the equation is X gas yields Y gas plus Z gas. When it's one-to-one stoichiometry, if all of the X was used up, Y would be 0.1 molar and Z would be 0.1 molar. But not all of the X was used up. In this case, we have a little bit of X left. In fact, we have this much X left. So the concentration of Y and the concentration of Z equal the initial concentration of X, 0.100 molar, minus the remaining concentration of X, because this has not been converted to Y and Z. Again, if all of it was converted to Y and Z, then they would be 0.1 molar, but a little bit hasn't. So it's 1.100 molar minus 7.26 times 10 to the minus 4 molar, which means that the part that has been converted to Y and Z gives a concentration of 0.0993 molar. Note this is only the case because there's one-to-one stoichiometry. So you can just simply subtract these two numbers in order to determine the concentration of Y and Z in the reaction mixture.